Not working. This. Hello, okay, let's get started. Hope everyone can hear me. So, does anyone has question from last time? Well, the Jing is not here. Okay. Anyway, it's time. Let's get started. So, there is no question. And the Jing is here. Let's add you to. Okay. Okay. Anyway, so yeah, let's go back to our Laplace transform. So a quick review from last time. So we start talking about this Laplace transform, which we kind of set up all the way. So this is a complex extension of Fourier transform. So in Fourier transform, we used to have the Fourier transform of some function equal to the integral of the function times e to the minus the complex exponential. So instead of e to the minus j omega t here, now we have e to the minus st here, and it can be an arbitrary complex number. So we think Fourier transform as integration on complex axis, on imaginary axis. Now we extend the integration to every complex number. So this transform is defined for every complex number s. And we think there is a transform back and forth between your signal x of t in a time domain and this Laplace transform big X of s in the complex plane, where s is possibly the whole complex plane. And there's a back-forth transformation. Well, we haven't talked about the back, or how do you calculate it. And important concept is this is the extension of Fourier transform, and there is this very nice relationship to build your Laplace transform back from Fourier transform. That is, if you are transforming on some complex number sigma plus j omega, where sigma and omega are both real numbers, so this is the real part of s and the imaginary part of s, then you can actually calculate this as the Fourier transform. It's a Fourier transform of this new function x of t e to the minus sigma t. Yeah. So yeah, you can kind of look at your Laplace transform on the sigma and the omega plane, and depending on which sigma it is, you can do a Fourier transform on the value of sigma. You just multiply your signal with this complex exponential, and then think about your Fourier transform on the axis, and you will get your Laplace transform. But the real weird thing about the Laplace transform is that the convergence is not uniform, and so you can write down this equation, you can define this equation for every s. But oftentimes this thing doesn't converge for every s. This is very from Fourier transform. Fourier transform, we think is convergent on some omega, we think it's convergent on basically all omega. Right? Although there are some weird things about like delta function, but we still think it's like something that works on every omega. For the Laplace transform, there is very distinct region of convergence concept. So for example, with Laplace transform, the Fourier signal is decaying exponential. Then we found out that it only converge when the real part of S is bigger than this minus A, minus of this A. Okay, and if you have decaying exponential in the other direction, it's decaying the negative time, then you will have a region of convergence that's bigger than negative A. Okay, so these ROC are very important for the Laplace transform. You can have same formula for you can have this same algebraic expression as a big X for different small x, but they are differentiated by they have different ROC. Yeah, so we'll spend a lot of time talking about analysis around ROC. So this feels annoying, but actually very useful in analyzing the property of your signals. And here we give an example that if you have your signal is a linear combination of two signals, then you take the ROC as the union of those two ROC. This is going to be a rule later when we actually talk about the properties of the Laplace transform. But it's pretty clear, okay. But it's pretty intuitive. And another thing with straight mono, although we kind of say the name already, is this concept of rational function. So rational function just means it's a polynomial divided by another polynomial. Okay? And as a fundamental theorem of polynomials, we know that a polynomial has roots. The number of roots of a polynomial equals to its degree, so there are some roots for this numerator polynomial, and there are some roots for this denominator polynomial. And the roots of the denominator will be called poles, because if you plug in those values, then x of s will diverge. And the roots of this n of s is going to be called zeros, because, well, plugging in there 0, then x of s is going to be 0. And then we start talking about RC more. Okay. jump. Oh, and we want to draw this root in a zero plane. We use this cross as poles, and the circle as zeros of your rational functions. Because the Laplace transform is actually pretty hard, most of our analysis will center around rational functions. So I think, yeah, almost every calculation we actually do is around rational function. And you can probably guess what's going on. You are going to do a lot of this partial fraction expansion. So then we come back to the properties of ROC. And the first property is that the ROCs are strips, and inside ROC you want this basically Dirichlet condition to satisfy. So inside ROC, this equivalent Fourier transform should be converged. So remember, we think about Laplace transform as the Fourier transform weighted with this e to the minus sigma t. And if you want this, if this is absolutely integrable, then this function is pretty convergent because of the Dirichlet condition. And usually that will mean it's inside the ROC of our Laplace transform. And I think obviously we are missing a lot of details where something bad happens if you satisfy the first Dirichlet condition rather than satisfy the other two. But we're mostly dealing with smooth or rational functions, so it should be fine. Okay. And then property 2 sounds like pretty dumb, but is useful. That is, your ROC does not contain poles of the rational functions. Just because the poles your function can diverge. So obviously that's not something in the regional convergence. And then there are properties 3, 4, 5, I believe. Yeah, 3, 4, 5 talking about, or actually 3 to 6 talking about ROC for how the shape of ROC is everywhere. Anyway, it should be ROC for some nice functions. Okay, so 3 says that if your function is really nice, so it's bounded at both sides, then the ROC will be everything, because once again, go back to now everything is 3 to 6 are all basically building on property 1. So you think about whether this Fourier transform of this thing will converge. This is x of s times e to the minus sigma t, whether you can actually get a convergent Fourier transform. Now, if your x is bounded at both sides, then however you, excuse me, how do I, okay, weird. Anyway, yeah, so if x is bounded at both sides, then you multiply the complex exponential, then nothing changes too much. You might get a big number, but it's a finite number, so everything is finite, the integral is going to be finite, and everything is going to converge, and your RIC is going to be everything. And there is an example that looks like it doesn't converge, but actually converge. And then there's a weaker condition where your x is only bounded on the left side, and the right side can be anything. Then once again, you do the exponential analysis, then you see that if you multiply it with the decaying exponential, then this integral is always going to be converged. So that means that your ROC will extend to the right all the way. Okay? So you get a bigger and bigger decaying. So you get decaying exponential, decaying faster and faster. It's going to be more and more convergent. And in more precise word, where is this? 3. Okay, it's 4. 3, 4, 5, 6. Okay, yeah. And yeah, so in terms of word, it means that if some point is in ROC, then every point to its right is also in ROC. And come up with property 1. Once again, property 1 says the ROC are strips. So whenever there's a point in ROC, all the points are up and down of it. The whole line containing that point is in ROC. So ROC will look kind of like a half plane, right? If you think about geometry, if a point is in, then it's all the up and down is in, and all the right thing is in, then only thing can look like is a half plane. And similarly, you switch left and right. Property 5 says that if you have a signal that's cut off on the right side as on time t2, then you multiply this growing exponential, which means decaying a negative time, then it doesn't make it more divergent. So the ROC should extend all the way to the left. So it's another half plane that cut off at this place, cut off at some place. And then there is property 6 says that if none of those satisfy, so your signal is kind of just a general signal that extends both ways, then the ROC is, this is a little tricky, but generally your ROC is going to be one strip, or if your signal is really bad, then there is no strip. There is at most one strip, it's either 1 or 0. And the proof is quite interesting. It's using the property 5, the previous two properties. So you are using property 4 and 5. So you cut your signal into two signals, that's right-sided and left-sided. And the right-sided says that the ROC is half plane extending to the right, and the left-sided signal has ROC that's left-sided half plane. And then you add those two signals together, then you once again use the linearity of Laplace transform. Then the Laplace transform of this signal should be Laplace transform of those two, and the ROC should be the union of those two things. So there are two possibilities. One possibility is if this is left of this. So if these two things actually have overlap, then you get this one strip in the middle. Okay? And if there is no overlap, then there is no strip. Okay? So there are only those two possibilities. Okay? So any question? Yeah. So there are four possibilities of ROC basicity correspond to how the signal look like. Although it's a little weird if you think about it, but let's not confuse you right now. So four possibility of the signal correspond to four possibility of ROC. So your ROC is everything where your signal is just a finite duration on both sides. ROC extend to the right all the way for your signal cut off at some point on the left, and or your ROC extend to the left all the way, corresponding to those kind of signal, or your signal extend to the both sides, correspond to one strip. Okay, so that's last time. Quick review. And okay, so let's look at the example of this kind of signal, where your signal extends to the both sides and see its ROC. And this is a very well set up example. So you have your signal is this complex decay, exponential decay to both the forward and the backward direction of your time. So we have a picture here. So yeah, so this is what your signal look like if your decay is positive decay, so p bigger than 0. Then for bigger t, then it's exponential decay, and for less t, it's also exponential decay. And if b is less than 0, then both exponential growth, so this is probably going to be pretty bad, as you can imagine. Okay. And then obviously you want to cut off. So when we talk about probably 5, yeah, probably 6, then the cutoff is arbitrary point. But if you see this, you probably want to cut off at the middle. So you have an easy calculation. So you cut off at the middle, and you have these two sides. So plus bt ut and minus bt ut and plus bt u minus t. And then this is the Laplace transform. Those two things we already talked about in example 9.1 and 9.6, 9.2. So there is some change of number there we need to do, but it's very similar. So anyway, so this thing we do exactly is one where it's plus b, and for this ROC bigger than minus b, and this thing is in 9.2, but we have a negative sign here, and I think you also need a negative sign here. But anyway, you do a negative sign correct, then it's this minus 1 and it's minus b. And ROC will be less than plus b. And then you can add them together, and you will get your Laplace transform. And the most important thing you want to know is you want to take the union of those two things. So you move things a little around, you see your RES. So you flip the left and right of this. Your RES should be bigger than bigger than negative b, and smaller than positive b. Okay, so this is your ROC, and you can visualize as this. You can bigger than bigger than negative b, and smaller than positive b. And if b bigger greater than 0, then you have this strip of ROC. And obviously, if b is less than 0, then there's no overlap, and your Laplace transform just don't converge anywhere. And you can kind of guess from here this thing should diverge whatever you multiply it with, whatever exponential you multiply it with. Okay. And so any question about this example? There is the left side ROC and right side ROC. left-sided ROC and right-sided ROC overlapping in the middle like this. And from here, you can also see some of the property vacancy links. That is, ROC is bound by these poles. Okay? And this is actually something specialized in rational function. Okay, so maybe you use this. Does this work? Rational? Oh, not bad. Yeah. And finally, we have those two property logs. We'll get on rational function. So the first thing is the RC are bounded by poles. And you need a little calculation to prove this. But basically, the rational function can do partial fraction expansion and calculate its Laplace transform, and you calculate it all, you found out it's always bounded by poles. And yeah. And so basically, you already know what the rational function Laplace transform, all the possibilities. So it's going to be when you do, it's a rational function, so there are a whole bunch of poles around the complex plane, and you will cut the plane into multiple strips. So maybe let me sketch a little bit. So let's don't talk about. So your complex plane and your rational function has a whole bunch of poles, and you can draw a straight line over them. And then your ROC is going to be one of the strips that separate by those poles. So your ROC is maybe here or maybe here, etc. Okay. And yeah, it's either some strips bounded by the pole or something to the left or something to the right. And yeah, the property 8 is basically combining this property with the previous property. So your vacancy is right-sided, you need to extend to infinity, so it needs to be right of the rightist pole and extend all the way to infinity. Or if your x-OT is left-sided, then you also need to extend to the infinity on left-sided, so it needs to be on the edge of the leftist pole and extend all the way to the left infinity. So any questions about the properties of ROC? Can I move this? Probably not. Okay. Anyway. Yeah. So that's rational function. We're going to see example to make this very clear. Okay, so here is the rational function. XOT big X over S equal to 1 over x plus 1 plus times x plus 2. And okay, so this is unnecessarily messy, but yeah, but here it is. So so we'll show. Okay, we don't have it. But anyway, so you can do partial fraction expansion of this thing. So it should be 1 raised plus 1 minus 1 raised plus 2. Anyway, so this thing has two poles. We want to see the pole structure of this. So obviously this thing has two poles. There's the plus 1 and the plus 2. Okay. And then there are 3 possibilities of ROC here. And they will correspond to different inverse Fourier transform. So we know the ROC needs to be a strip that bounded by poles, so as we said. So it's either rightmost strip, or in the middle strip, or leftmost strip. So there are 3 possible ROC, and they will correspond to 3 different inverse Fourier transform. And I believe okay, then how do you do this here? But anyway, and they basically correspond to how you do the inverse Fourier transform around those S plus A. Remember in the So it's still all the way back to example 9.1 and 9.2. We have those two different complex exponentials, so exponential decaying in a positive time and exponential decaying in a negative time. They all have this 1 over s plus a Laplace transform. And I should move this. No. Okay. So we have this thing has ROC plus RES that's less than negative a. So yeah. So we think about how this thing can transform back to either this or this around the pole at -1 and the pole at -2. And so each pole has two possibilities, or each partial fraction expansion has two possibilities, and there are four possibilities here. And so you think about how the ROC of those two terms overlap with each other. So if both poles you are picking the positive side, so both the positive decay, then you will get this ROC, right? So the overlap will be this ROC. So this signal will correspond to this ROC. And if we have the left one picking the right side ROC and the right one picking the left ROC, then the overlapping is in the middle. And that is so positive, negative, I think is this one, right? So this signal will correspond to this ROC. And if both of them picking the negative direction, okay, then the ROC overlapping will be on the left side. So we know this 9.52b will correspond to this ROC. And now we have an extra. That's on this pole you pick the left hand side, and on this pole you pick the right hand side. And there is no overlap, so it corresponds to no ROC. That means this thing never converge. And yeah, so this thing just don't have a Laplace transform. Okay, did I get it right? No, I think I get it wrong. Which one? Okay, so this one is actually a one that has no ROC because the -1, -2 to the left, and the -1 to the right. Okay, so D is the one with no ROC, and the C is the one with overlap, I think. Yeah. So we have the -1, you are picking the. So -1, you are picking the left hand side, and the -2, you are picking the right side. Okay. Yeah. Anyway. So you can see that you have different ROC. You will correspond to different inverse Fourier transform. I should have. Okay, let's do. We should write the equation here, right? Right here, this is equal to make it should have do this, but to make it more clear. So this is equal to 1 over s plus 1 minus 1 over s plus 2. And so this thing corresponds to the -1 pole, and this thing corresponds to the -2 pole. And we're thinking about if you choose different ROC for those two poles. So each of those poles has these two choices, and we're thinking about all the combinations. So there are 4 combinations. There are 4 combinations to invert x of t. And so 3 of them will correspond to the 3 different ROC choice, and 1 of them has no ROC, so it doesn't make sense. So it just don't have the Laplace transform. So, question about this example of rational function. So this is going to be a glimpse of how we are going to do inverse Laplace transform. And for rational function, you do partial fraction expansion, and so each term you just use those two formula to do the inverse. Then you use the ROC analysis to see whether this one is picked or this one is picked. Okay. Yeah. Okay. For convenience, let me write this here too. So this is RES less than negative A. Okay. Now, okay, so that's ROC. Oh, how do I? Oh, okay. Yeah, so those two are very useful. Okay. And yeah, then let's go to the inverse Laplace transform. So there are two methods to do inverse Laplace transform. One is brute force calculation, which we'll talk a little bit, but we don't know how to actually do it. But it's very formal. And I guess both of them already talk about. One is basically you do the inverse Fourier transform using the relation we have been talking about, because you can think about Laplace transform as the Fourier transform of a signal times e to the minus sigma t. And the other thing is for rational function, you can do fractional decomposition, which I already do here, and you just pick side for each fraction using the ROC analysis. Yeah, let's have a more formal discussion of all this. So the first way to do inverse Laplace transform is you do inverse Fourier transform because Laplace transform for some x equal to sigma plus j omega is a Fourier transform of x of t times e to the minus sigma omega, excuse me, f of x of t times e to the minus sigma t. Yeah, and yeah, so that's something. But anyway, so we have a Fourier transform of a signal, then we know how to do inverse Fourier transform. So we can get what's x of e to the sigma t as the inverse Fourier transform of this thing, and have the formula for inverse Fourier transform. So it is 1 over 2 pi minus infinity to infinity, and this big X times e to the j omega t d omega. I guess it's now we don't know how to do it. Well, I guess we know how to do it, but so you can calculate this like Fourier transform. So if this big X is nice enough that you can do this integral, then yeah, then you can do the inverse Laplace transform. And so you get this thing, then you just multiply both sides by sigma t. And sigma t actually doesn't affect this integral, right? Because you don't have omega here. So you just calculate this and then you multiply by sigma t, then you can get your x of t. I guess that's okay. Okay, and yeah, so you multiply both sides, but we want to make it look a little nicer. So you can, it doesn't depend on omega, and you can put it inside. So, and you compare exponential, so you have e to the sigma plus j omega t here. And then you can make things. So, oh, there is a question. Okay. E of t 的 e to the actually sigma not alpha， 把 e to the sigma t 直接到积分里面合法，因为 because it doesn't depend on omega, it's just like a constant. E to the sigma t has nothing to do with omega, right? Sigma and omega are independent. You think S is kind of two independent variables. One of them is omega and another is sigma. Okay. Yeah. So yeah, so you can just put it inside. And now we can write this. Now we can write this in a prettier form, but that might confuse you. Now, yeah. Now you see the sigma plus j omega and sigma plus j omega here. And you remember it's equal to sigma plus j omega, so why don't I just write this as S here? Okay. Yeah. Okay. Anyway, yeah. So now if this is just the integral of the omega, we kind of know what it is. It's using omega as a real variable, and you just integrate through the line of omega. Okay. Now I make this a little more confusing. Now we group the sigma positive omega together, and so those together become a complex number S. And now this integration phase. Now, yeah. But sigma is still kind of constant. We're only integrating over the omega, and ds equal to j d omega. Okay, it should be omega. But anyway, so ds equal to j d omega, so you can change the omega to 1 over j ds. And now we have this weird thing. So omega is from negative infinity to positive infinity. And I think about how this effect is. It should be S from sigma minus infinity and sigma plus j infinity, right? Okay. And so this is kind of well defined. This is still well defined, but it's now something called the contour integral. You're integrating over a complex number. And complex number is something on complex plane, and it's when you're integrating them, you need to pick a place like here. Okay, so let's see it here. And yeah, so we think like where Laplace transform has some ROC, and we're integrating over some S that from we are integrating some S that's sigma minus j omega to sigma plus j omega. Okay. How do you say? Okay, yeah. So some sigma here, and so yeah. So S is in this complex plane, has real and imaginary value, and when you do a complex integral, you need to pick about the pace of the integration. And here is this pace where you write some sigma and you integrate from sigma negative infinity to sigma minus j infinity to sigma plus j infinity. Okay. And okay, so now disclaimer first. So this course is not complex analysis, so we will not teach too much about this contour integral. So if you want to know how to actually do contour integral, you need to take a complex analysis course. But let's say a little thing about this thing. Easy thing we can say. So first is that this integral is now it's kind of weird, right? Because you have sigma here, and sigma is kind of arbitrary. It just need to be something inside this ROC. Okay, sigma is arbitrary inside ROC, and that better means that this number doesn't depend on sigma as long as sigma is in ROC. And that's true because of the property of the contour integral. So those complex integral, we call it contour integral because it's usually some weird place inside the complex plane. And when we do this contour integral, a lot of time you want to integrate around some loop. And a very good theorem about this is that if you integrate around a loop, and if that loop contains no singularity inside, so basically no poles, if we are talking about rational function, so no poles inside, then this integral will be 0, because when, that's not totally wrong, okay. And by our characterization of ROC previously, we know that when we have a rational function, are we supposed to have a rational function? Not quite. but I think it is true here, right? For every function, right? Because for every function, then the RC shouldn't contain any poles inside RC. Because poles diverge. Because it poles the Laplace transform diverge, and your RC cannot contain anything diverge. So it's very nice inside here. And so if you do a weird loop around infinity, then this whole loop should be 0. And that means that if you integrate over this line, and it should be equal to, you go to here and integrate all the way to the top, then integrate back. Okay, and the other way to say about this is, so if you are integrating over a very nice area, there is no poles, and you take a loop, then the integration will go in 0. That means that if you cut this loop into two sides, into two parts, and so the left part and the right part, then this integration should equal to this integration. Okay, so this integration should equal to arbitrary integration inside LC. So you don't even need to be a straight line, just the integration from negative infinity to infinity. And yeah, that should be equal as long as, so there should be a weird negative path like this, right? So as long as this weird infinity part is also 0, and that's going to be true most of the time. It's a little weird, yeah. I think that's yeah, that should be true if you want the Fourier transform to converge. Yeah. Anyway, that's a little bit of contour integral, and we'll not actually teach you how to do this thing. This is something interesting to know. And you can integrate over any negative to positive imaginary paths inside the RC if you know how to do contour integral. Or you can kind of brute force it with this real d omega integral. Okay. But I think that's the most we'll talk about is general form. Any question now? 我们遇到的都是解析函数，应该是吧？我们都不想什么太奇怪的函数，解析函数的analytical function 嘛，应该是。But anyway, yeah, we are going to restrict to very high restriction. We are going to restrict to the very special case of rational functions. Okay, so a polynomial divided by a polynomial. Now things are very easy. We restrict to the rational functions. Then the inverse Laplace transform is pretty easy. You can just do partial fraction expansion. You don't need to do any integration. Okay, just look up table like what we did for the Fourier transform. Look up table and then invert it into a whole bunch of complex or real exponentials. Okay. So if there is no poles, so yeah. So if a rational function, then you can basically do partial fraction expansion of your rational function into those partial fractions. It's 1 over s plus ai, where ai's are the poles. And yeah, so if there is no higher order poles, then you can all break down to this first order partial fraction. And okay, so then for Fourier transform, you look out table of this thing and you do inverse, then it's done. But for Laplace transform, you need to do this ROC analysis, because there are two functions that has Laplace transform equal to this 1 over s plus a. And once again, they are the example 9.1 and 9.2. So you need to look at the ROC. So if you are picking the right side ROC, then it's this positive exponential decay, and if it's the left side ROC, then you pick up this negative side exponential decay function. Okay. So you look at the ROC of the total thing, then you think about how the inverse transform. Then you think about how the ROC of each individual term should be. Okay. So maybe let's look at example. Okay, so this thing back once again. Yeah, which we basically already solved. So yeah, once again, this x of s equal to 1 over s plus 1 and s plus 2. And we're going to solve the inverse transform of these for different ROC. And do we have a picture here? It's really annoying. Okay, the picture here. So once again, this thing has two poles, a -1 and a -2. And we pick the ROC equal to bigger than -1 here. And then we do partial fraction expansion. So it should be something over s plus 1 plus something over s plus 2. And we just eyeball before, but so we can solve it here. And once again, you can solve this by brute force multiplying out everything. But here we use some trick that's a little smarter, will be a little faster. So you can solve A like this. It is like without solving the linear equations. So you multiply both sides by s plus 1. Okay? So x plus 1 x of s. And so this s plus 1 will cancel the s plus 1 downside, so you get s plus 2 here. And you have 1, and also s plus 1 cancel. So you get a here plus, and I didn't, okay. So a here and s plus 1 over s plus 2. And so why do we want to do this? Because now you see only this term has this s1 plus s plus 1, right? Because s plus 1 gets cancelled by the 1 over s plus 1 on those two terms. So if you pick s equal to -1 here, then this s plus 1 becomes 0, and this b term just disappear. And so you just get a equal to s plus 2, plug in s equal to -1. So that's -1 plus 2 equal to 1. So you can calculate a equal to 1 from this thing. So it's not necessarily that much faster than do the multiply out. And yeah, but anyway, so you can similarly do this kind of calculation to get, you can do this kind of calculation to get B. Okay. So you can do partial fraction expansion anywhere. You get x over s equal to this 1 over s plus 1 minus 1 over s plus 2. And for those two terms, then we try to do the invert, and you want to decide whether you want to pick so each of those two terms. So one of them has point -1, one of them has point -2. Then you need to decide whether you want to pick the right side ROC or left side ROC. Yeah. And yeah, so now we need to look at the ROC given at the very beginning. So ROC is this bigger than -1 thing. Then this should be the union of the two ROC we pick here. Then the only possibility is both of them you pick the right side. Okay. Yeah. So you know both of those ROC you need to pick the right side one. So the bigger than -1 and the bigger than -2. And so the invert is the positive decay for both of them. Okay. Any question about how we do this inverse Laplace transform? Inverse Laplace transform. So basically, you do partial fraction expansion, and each turn there are two possibilities. You either use this invert or this invert. The difference is ROC. So we need to look at the ROC of the original function, and you think about how you can get this ROC as a union of the RLC of the partial expansions, and yeah. And so from this RLC, you decide RLC of the partial expansions. Then once you have the RLC of the partial expansion, you can just invert those partial expansion using one of the two formula. So here we are picking the both right side. And then the next example, obviously we are going to pick a different RLC and get a different invert. And do we have a picture? No, we don't have a picture. But but anyway, so we have another example. So now we have the example of picking the RLC that's the left side RLC, left side of everything. Okay, so we don't have a picture, but you can kind of imagine it's the left side of everything. Then it's just reverse left and right. Then the RLC of those two partial fractions need to be both picking the left side. So both picking the left side, then you get two of those negative decaying exponential. And so both of those u minus t. And then you get the invert Laplace transform. And obviously you can also have an example, although we don't write here, I think. Oh no, it's here. Yeah, we have another example. Then we'll pick the middle side RLC. Then you get the right-sided RLC union with the left-sided RLC. Look at the picture. So if you want to have the middle part, then you need to pick the left side of this and the right side of this. So right of this and the left of this, your union will be the middle part. And yeah, so that's your inverse. So left-sided and right-sided together. So any question? Oh, just in time. And yeah, you can see that this is easily extended to a general formula. We can talk about this later. Question? Or it will be time for the class? No? Okay. Then let's stop.